6.3. Lesson 3 is about polynomial functions. So today we're going to be talking about their graphs. So our goal is going to be to evaluate polynomial functions and identify the general shapes of the graphs of polynomial functions. So we're going to learn to evaluate them and kind of learn an idea of what their graphs are going to look like. A polynomial in one variable, it's an expression in the form, and this is going to look really confusing, so bear with me. It's a sub n x to the power of n. Okay, I'll go through this in a minute. And then plus a sub n minus 1 to the power of x, times x to the power of n minus 1, plus dot, 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 all the way to a2x squared plus a1x plus a sub 0. I probably should have wrote that underneath. Let me make that look a little better. That looks much nicer. All right, then all of your a values are just real numbers, okay? They're the coefficients. The reason why we don't do a and then b and then c and then d is because we could eventually run out of letters, right? A through z, we only have 26 of them. You could have a polynomial to the 32nd degree, and then you would have run out of letters. So instead, we use a, but the subunit on a tells you that each one of these are different variables. Okay, so this could be a 4, this could be a 7, this could be a 6, this could be a 5, this could be a 2. The a's just are representing different numbers. Okay, they're just showing you that those are all different variables. It's kind of like when we did quadratics. We did ax squared plus bx plus c. We used a, b, and c, but our problem is we don't want to run out of alphabet. So instead, we just stick with a and we just number them instead. So that just tells you that those are all being numbered. Okay, x to the power of n. Okay, it depends on if you were going x to the 32nd power. This would be x to the 31st power, and then x to the 30th power, and then x to the, it counts down. So that is a polynomial in standard form because you go from the highest degree to the lowest degree. Okay, which the lowest degree is 0, which is just that constant term at the end. So this would be plus some number. There's no x there. Okay, so a is going to be some form of a real number. Okay, you'll have some form of a real number that is your coefficient, and n is an element of a natural number. It's like 1, 2, 3, 4, 5, because to have an exponent, it has to be a positive counting number for it to be a polynomial, right? Remember we talked about that, no negative exponents. So we use natural numbers for the exponents on the end. So that's just what those mean. All right. So our leading coefficient is always going to be the very first coefficient, the one that goes with the highest degree. So in this case, in our general form, it is a sub n. It is the first coefficient when the polynomial is in standard form. Okay, so as long as it's in standard form, your leading coefficient is the number that is out front. Okay. A polynomial function, I'm just going to put an example here, is something like f of x equals some form of this. So I'm just going to write an example. 4x to the third minus 7x squared plus 2x minus 4. Okay, I just made it up. It was not given, I just literally made up numbers. So that's an example of what a polynomial function might look like. Okay. Now a power function, is just one term. So it's like y equals, or f of x equals a sub n x to the power of n. Okay, so it's just one term. You're not adding a bunch of stuff. So an example here would be like f of x equals 7x to the 5th power. That's a power function. It's only one term. You're not adding a bunch of, you don't have a chain of terms there. It's just one term. And the end behavior is the behavior of f of x as x goes towards negative infinity and as x goes towards positive infinity. So what this means is as you look to the left, if you're looking on the x-axis and you're looking for negative infinity, you'd be looking to the left. If you're looking where x goes towards infinity, you're looking on the x-axis, that's going to be off to the right. Okay, so it's the behavior of the y, okay, as you move to the left or move to the right. So we will see what I mean when we get to some examples. But that's just the vocabulary you want to make sure you have down. So we have some examples here where we're going to look at the expression, the degree, and the leading coefficient. This term right here, we call that your constant term. Okay. That last term is always just a number. That's a constant. Because there's no variable to change it. It's constant. This here, that's a linear equation, right? We've learned about those. That one's linear. What do we call it when we go all the way up to x squared? Anyone remember? Quadratic, yeah. So that one's quadratic. If we go up to the 3rd power, what do we call those? These are all polynomials. Okay, they're all polynomials, but the more specific, if it's going to the 3rd degree, this one's cubic. Just like we would say 8x cubed. Okay, that one's cubic. And then this is just the general form. Now we practiced in 6.1 how to find the degree of a polynomial. So looking here at 8, what's the degree of this polynomial? 0. Okay, doesn't have any variables, so its degree is 0. What's the degree of this polynomial here? 1, because the highest degree term, so this has a degree of 1, this has a degree of 0. The highest one is 1. How about the quadratic one? What's the degree there? 2. This has a degree of 2, a degree of 1, a degree of 0. 2 wins, it's the most. This has a degree of 3, 2, 1, 0. What's the degree overall of this polynomial? 3. And what's the degree of this general polynomial? What's the biggest exponent? This one doesn't have any. This one has an exponent of 1. This one has an exponent of n minus 1. And this one has an exponent of n. N is going to be the largest one. That's the largest exponent. Okay. So then we're going to go through and we're going to find what the leading coefficients are. The leading coefficient is the coefficient that goes with the term with the highest degree. So this one has what as a leading coefficient? 8. Okay, this has what as a leading coefficient? 3. It's just the number that's in front of the term with the highest degree. The x squared was our highest degree. What's the leading coefficient? -6. How about for the next one? 8. And how about for this last one? A sub n. Very good. Okay, so that's going to be the big thing. Now, I gave these to you already in standard form. Are they all going to be given to you in standard form? No, you'll probably want to look at your problem and rearrange it so that it is in standard form. So going from highest degree to the lowest, rearrange those terms. Okay, and that's why we practice that. All right, so now that we know how to identify the degree and the leading coefficient, we're going to kind of take a break from those vocab terms, and we're going to look at how to evaluate a polynomial. You'll notice that there are some fake story problems in this section. By fake story problems, I mean you really don't have to know what the heck is going on in this story problem for you to be able to do the math behind it. Okay, a lot of people see a story problem and they say, oh, it's scary, it's going to come off the paper and eat me. It's going to bite my head off. It's not going to happen, I promise. It can't come off the paper. If it does, you'll have to show me because I've never seen that happen before. Okay? Maybe it would make life a little bit more interesting, I guess. But all this is it says blah, 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 by, oh, look, that looks like some key information there because it's a function. Cool. Blah, 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 blah. Blah, 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 blah. Okay, maybe I should probably look at the numbers that it's giving me and figure out what's going on. Find the volume of air. So it looks like I'm trying to find volume. So I'm just going to write that down. The volume is unknown. I'm looking for the volume. That's unknown. 2 seconds into the respiratory cycle. Okay, so that means I have a time equals 2 seconds. All right, well don't know what this is even talking about, but I know that I don't know a volume. I know that the time is 2 seconds. Are you with me? All right, let's read now. It says the volume of air in the lungs during a 5-second respiratory cycle can be modeled by, okay, there's the model. V is the volume. Oh, look, I don't have the volume. And T is the time in seconds. Oh, look, I have the time. So all I'm going to do is I'm going to take this equation, or this function that's given to me. I'm going to not fill in V because I don't know what that is, but I'm going to fill in the time is 2. So when I fill this in, V of 2 equals negative 0.037. T is 2, so I'm going to fill that in, cubed, plus 0.152. The T I don't know. Oh, wait, I do. It's 2 squared plus 0.173 times the T I know is 2. Okay? Now, all this is calculator work. I'm figuring out the volume at 2 seconds equals, plug that into your calculator exactly how it looks. So, plug it in. Negative 0.037, 2 in parentheses, to the power of 3. Make sure you're using the caret to the power of. Caret button looking like this. Guess it looks like a carrot top or something. So go ahead, fill that out, and let's see what we get. So we're finding that V of 2 is 0.658. Now the one thing I want to double check is how is volume being measured here? Volume is in liters, so I want to make sure that I make it look like I really paid attention to what the heck was going on in the story problem, and I make sure to put a unit on there. So that's my answer. The volume at 2 seconds is 0.658 liters. That's that. All right, ready to flip the page? So you have to know how to plug things in. All right. Next, we're going to talk about evaluating at a function. So, g of 2a. So what we're going to do is we want to take our g function and plug in 2a instead of x. So I'm going to write out my g function. And we've done problems like this before, right? So I'm going to write out my g function. It is x squared minus 5 times x plus 8. I write it out like that first. It's exactly what I wrote here. I just put parentheses everywhere there was an x. So far, so good. So I have x squared minus 5x plus 8. And then I want to go through, and what did I replace instead of g of x? I now have g of 2a. So instead of x, I'm going to replace all those x's with 2a. Well, now I'm just using a little bit of what I did in section 1, because what is 2a squared? And so many people tell me it's 2a squared. It is not. It's 4a squared, because remember, you have exponents of 1 on both of those. So it's 2 squared a squared, which is 4a squared minus, what do I have here? 10a plus 8. Okay, so far, we're doing okay. Now number 2 says 3 times g of 2a. Well, wait a minute. I just figured out what g of 2a is. G of 2a was equal to 4a squared minus 10a plus 8. Right? Is that okay? So when I have to figure out what 3 of g of 2a is, I already know what g of 2a is. I've already done it. So I'm going to take 3 times the g of 2a is 4a squared minus 10a plus 8. That's just a problem from section 1. What do? Distribute. So you're going to distribute that 3 to all terms. So we get 3g of 2a is going to equal 12a squared minus 30a plus 24. Give me a 1 through 5. How do we feel about those two problems? Okay, now the next one gets a little bit trickier. It's very similar to what we did in number 1, but this time what we're going to plug in is 5a minus 2. So again, we're going to take that g function. I'm going to rewrite it. We have x squared minus 5x plus 8. Okay. What did we replace for x this time? 5a minus 2. So that's what we're going to plug in. Now, 5a minus 2 squared. Many people mess this up, because what you actually have here is 5a minus 2 times 5a minus 2. It is not just a monomial anymore. So we have to distribute. We're going to have to FOIL. So first times your first is 25a squared. Your outside minus 10a. Your inside minus 10a. Your last plus 4. I'm going to combine like terms. 25a squared minus 20a plus 4. That's what that first term turned into when we squared 5a minus 2. Minus, we still have this term here, which I can distribute, minus 25a plus 10. And then I still have that plus 8. I no longer need parentheses around this. However, sometimes you have a coefficient out front, so you want to keep your parentheses there just in case. Okay? In this case, since it's just, there's nothing out front to distribute, I can get rid of the parentheses because it's just a chain of terms that are adding or subtracting. Now go through and find like terms. 25a squared, I don't see any other ones like that. So I have 25a squared. That one's done. Negative 20a and negative 25a minus 45a. Those are done. I have 4, 10, and 8. 22. and that should be done. So g of 5a minus 2 equals that polynomial that I found right there. Are we okay with that so far? Now this last problem, I'm going to take g of 5a minus 2. Wait a minute, didn't I already find that? G of 5a minus 2 was this 25a squared minus 45a. And 3 times g of 2a is what I found in number 2. Are we okay with that? Do you see how we already did those problems? So what I'm going to do is I'm going to take the yellow and add it to the green. And we'll see what we get. So the yellow was 25a squared minus 45a plus 22. And the green was 12a squared minus 30a plus 24. Now if I'm just adding 2 polynomials, what do I need to do here? I'm adding 2 polynomials. Combine like terms, that's it. Do you need the parentheses? Nope, the parentheses don't mean anything. So I get rid of those parentheses and I just combine the like terms. 25a squared and 12a squared. 37a squared. And negative 45 and negative 30 is negative 75a. 22 and 24 is 46. And that would be my final answer. Does that look okay? So that's how we evaluate functions, but add a, or evaluate polynomial functions at variables. Okay, so you have to be able to evaluate polynomial functions, not just with a number, but with also variables. Can I go ahead and turn the page? Or questions on this before we do? All right. So let's look at how to evaluate a polynomial function. The general shapes of the graphs of several polynomial functions show the maximum number of times the graph of each function may intersect the x-axis. Okay. This number is the same number as the degree of the polynomial. And you guys have already looked into this a little bit. Oh, let me zoom out on that. So what this is saying is if your polynomial has a degree of 2, it can only hit the x-axis twice. Well, a quadratic function has a degree of 2. And you guys know this because when you guys did the graphs, remember they were parabolas like this? And the max number of times it can hit the x-axis is 2. So that's what it looks like. Now when we get to the cubic function, which has a degree of 3, its max number of times it can hit will be 3 since that's the degree it is. So it starts kind of like how the parabola started, but it can turn again and go back up in order to hit 3 times on your x-axis. That's what it's saying, is the degree determines the number of times that it can hit that x-axis. Right? It doesn't have to, because as we know that the parabola could have happened down here, and it might not hit the x-axis at all. So it may be anytime between 0 and that maximum number. Okay. What's a linear function, though, look like? It's just a straight line. So on this one, when you draw in that straight line, it's just that diagonal line, it can also only hit a maximum of 1 time on that x-axis. That's what we're looking for, is how many times does it hit the x-axis, that horizontal axis. Okay, that degree is 1. A linear function has a degree of 1. Y equals 7x plus 4. Are you guys with me on that? All right, so then we have a constant function which has a degree of 0. That would be something like y equals 4, which is, those are those horizontal lines. Like y equals 4 is horizontal line. It doesn't hit that x-axis at all. 0 times is how many times it can hit that x-axis. Okay. A quartic function would have a degree of 4. So very similar to this, but we're going to add one more term in it. And it hits it 1, 2, 3, 4 times. Quintic function has a degree of 5. What are we going to do? Add another term. There it hits once, twice, 3 times, 4 times, 5 times. Might even have to extend my x-axis because I got a little crazy there. But 1, 2, 3, 4, 5 times is the maximum number of times it can hit. Now again, it doesn't have to hit all 5 times, but it can hit a maximum of 5 times. So let's kind of write that up here. The degree is going to be equal the maximum number of x-intercepts. The degree is equal to the maximum number of x-intercepts. That's what that little small paragraph there is saying. The degree of the polynomial is the maximum times that it will hit the x-axis. Okay. Now, we have some information that the degree of the polynomial and the leading coefficient give to us. The leading coefficient tells us very important information because the degree of it, okay, the degree of the polynomial, if it's even, then the end behaviors are going to match. You'll see why in a second, because this is going to kind of sound like foreign language to you for a minute. If it's even, the end behaviors match. If it is odd, the end behaviors are opposite. Now let's look at those examples that we just drew in, and I'll kind of show you what I mean by that. Here the degree is odd. Do you see that? See how the degree is odd here? One of your ends goes up, the other goes down. With an even degree, though, they both go down, or they might both go up, but they match. Here it's odd, they go in opposite directions. Here it's even, they go in the same direction. The end behaviors are what the ends happening after all the little loop-de-loos that it does, or ups and downs, I guess, that it does in this central part of the graph. Does that make sense? Eventually it quits going up and down, and it has an end behavior that it's going to continue to go up forever and ever and ever. It continues to go down forever and ever and ever. And if it is odd, they go in opposite directions, but if it's even, they go in the same direction. Are we okay on that idea? All right. Then the leading coefficient, that is what's going to tell us what happens on the right side. If the leading coefficient is positive, this will tell you that the right goes up, which is toward positive infinity. If the leading coefficient is negative, that's when the right goes down, which is toward negative infinity. And if you play around with this, you'll find that odd degree functions will always have an odd number of real zeros. Where if it's an even degree function, it has to either have an even number or it could have 0 real zeros. Remember, zeros are those solutions, x equals, instead of the x-intercepts, which are written as points, but they come from the same idea, right? An x-intercept is how you find a 0 from back in when we were solving by graphing with quadratics. All right, so we have a couple example problems on the back that we're going to actually go through. So if you flip this over, nope, not that one, flip too many pages. The first thing that you want to do is identify which one is your leading term. Which has the highest degree? Is it this first term, the middle term, or that last term? This one, it's the first term because it already put it in standard form for us. Okay, but you always want to double check. So I always circle that good term that I need to be paying attention to. What's the degree of this polynomial? 2. And what's the leading coefficient? 3. Now, these tell us information. So the leading coefficient is what you want to look at first because you can draw in what's going on the right side of your end behavior here. So your leading coefficient is 3. That means it's positive. What happens if your leading coefficient is positive? The right side does what? It goes towards positive infinity, so it goes up. So I just draw it in just like that. I don't really care what's going on in the middle. That's where that question mark happens. Okay? Then we look to the degree. The degree, is it even or odd? It's even. So what does that tell us about the other end behavior? It's going to be in the same direction. Since that one went up, this one goes up. Now we get to write our end behavior. And the way that we write it is as x goes towards infinity or as x goes towards negative infinity. Okay? This tells you your x-axis moves left to right. So where is x positive? On which side? The left side or the right side are x positive? The right side. So as you look on the right side, f of x goes towards, is it going up or is it going down? Up. And is up positive or negative? Positive. So it's going towards positive infinity, not negative infinity. So this is a sentence. It says, as you move to the right on the graph, your graph is going to move up. As you move to the right, you move up. Do you see that? So that's how you tell your right direction. As x goes to the left, it's looking at the left side now. Does that one go up or down? Up as well. So again, it's going to go towards positive infinity. Okay? Then we can state our domain. The domain are your x values. Does it move to the left and to the right? Yes. So it's x is an element of all real numbers because we move both to the left and to the right. Now for your range though, do you go up and down on your range? No. So that means somewhere here you're going to have a minimum value. So you know that y will have to be greater than or equal to whatever a minimum value is, which we don't know right now, but we know that there is a minimum. That's what your range would look like. You guys want to try the next one on your own. Use those notes and try the next one on your own. All right, so if you got your degree, we should have 3. You got your leading coefficient, it should be 1. The right side should be going up, and the left side should be going down. Did we get that far? Raise your hand if you got that, if that's what your sketch looked like. Okay, good. Now, this next part, I filled in what's the same every single time. This is going to be the same every time. As you go to the right, we have to know what f of x is doing. As you go to the left, you have to know what f of x is doing. As in your y, is it going up or down? So that's going to be the same every single time. As you go towards the right, so as we go to the right, positive infinity is right. Which way is your y value going? Is it going to go up or down? Up. So up is positive infinity. As you move to the left, though, what way do you go? Down is towards what? Negative infinity. Is that language starting to kind of come together? Kind of figuring it out. So what I wrote in black is going to be the same every time. You just have to fill out positive or negative infinity where I put the red in. Okay, do we have questions there? Yes?
So like on a quiz or like an assignment, you can write that out?
You'll have to write that out, yes.
Just the black or the red or both?
Both of them. If it's asking for you to describe the end behavior, this is a sentence that you have to write.
Okay.
The black will be the same every single time. The red is what you're going to have to fill in. Okay, but you will have to write out that sentence. Yes, Avery?
This might be a stupid question, but how do you know, so for the side that's going down,
Uh-huh.
how do you know it's not like flip, or it doesn't go this way?
How do I know it's not going up?
No, like it's going, so let's say it went this way. Like down, it's still going
Oh, like down this side?
Yeah.
It's not, because you have to have something on the left, you have to have something on the right.
Okay.
So you're not going to have 2 things on the right, okay? Because then it wouldn't be a function. You wouldn't be able to draw that vertical line test through it. It would hit it twice, right? So you have to have something on the left, something on the right. The right side is from your leading coefficient being a positive value. We knew it had to go up. And then this says whether it's going to do the opposite thing or the same thing. Since this is odd, it's opposite. I remember odd opposite. Both start with O, so that's how I remember. So degree being 3, the left side has to do the opposite from what the right side's doing. Huh. All right, let's talk about the domain and range here. Do you go both on the left and the right? Yeah, you're going to have to do that every single time. So for your domain, you're going to have, again, x as an element of all real numbers. Your range, do you go both up and down? So you're going to cover all your y values too. So y will also be an element of all real numbers. And that one's done.
It's only an element of all real numbers on the range if it's not.
If it's going in both directions. Has to go in both directions to cover the whole number line. Okay. Here, you knew you would be having a minimum value since you only go up. So whatever might be going like this on the inside of there, we have no idea, but somewhere in there is a minimum value that it hits. So it goes from that minimum value all the way up to infinity. Okay. Try to figure out, again, the degree, leading coefficient, and your sketch on this next one. Then we'll check it. All right, let's see what we got. This is what I got. And I made little notes here, too. You don't have to make the notes, but sometimes people like to do that. It helps them out. So my degree was 4. My leading coefficient was -1. And both sides are going down. Raise your hand if you were able to come up with that sketch. Good. So the leading coefficient is what you look at first. It was a negative, so I know that the right side has to go down, so I drew the right side in first. Then I looked to my degree, and my degree was even, so I know that my ends have to match, so I needed to draw the left side doing the exact same thing. Go ahead, Avery.
If it's negative, does it always go down?
For your leading coefficient?
Yeah.
Yes, negatives go down, positives go up. That's how you know what to do with the right side. Okay. And those are your rules that we wrote right in here. So the degree tells you if the end behaviors match or are opposite. The leading coefficient, that number, if it's positive versus negative, tells you if the right side's going up or down. So that's how you figure that out. Does that make sense? Okay. All right, so then we have to fill in our end behavior, describing our end behavior here. So as x moves to the right, so we look at the right side, where's f of x going? Positive or negative infinity here? This one's negative infinity. Okay, as we move to the left, what's going on the left side? Where is f of x going? Negative infinity also. Because our end behaviors have to match. What's your domain here? Your domain is your x values. They move left to right. Do you move both left and right? Yep. So what's your domain going to be? All real numbers. So x is an element of all real numbers. Your range, though, does it go up and down? Not on this one. It just goes down. So what kind of value are you going to have in here somewhere? A maximum. So how would we write the range? Yep. Y is less than or equal to, because it eventually touches that maximum, your maximum. Let's try this last one. Fill in the degree, leading coefficient, and the end behaviors. All right, so if you filled out everything, this is what I have. The degree is 5. The leading coefficient is -6. As you move to the right, your y values go toward negative infinity. As you move to the left, your y values go toward positive infinity. The domain is x is an element of all real numbers, and your range is y is an element of all real numbers, because you go both to the left and right, and you're going both up and down. Raise your hand if you got everything on that. Give me like a 1 through 5. 5, I got it, I'm good. 4, I got most of it. Have a little work to do. Where are we at? Coolio. Awesome. All right, so these last two, they are giving us, do you have a question? Go ahead.
Why isn't it vice versa? Like with the way the arrows are going, why isn't it starting out down?
Because the right side, the leading coefficient, tells us what the right side is doing.
Oh.
So if it's negative, the right side has to be going down. And then since it's odd, the left side does the opposite. Okay, so you have to do the right side first. Always the right side is the right way to go. Okay? All right, so these ones, they gave you a graph, and then we have to figure this out. So describing the end behaviors, as x goes towards the left, what's f of x doing? I switched them up this time. Sorry if you were in the habit of the other way. So as you move to the left, if you move to the right, we have to know what f of x is doing both ways. So let's fill it in. As you move to the left, what's happening on the end with the left side? It goes down. Down is towards negative infinity. As we move to the right, right's positive infinity. Okay, which way is your y value going? Up, which is towards positive infinity. So looking at this, are the ends odd or matching? Are they doing opposite things or are they matching? They're opposite. So is your degree odd or even? Odd. How many real zeros are there? How many times does it hit the x-axis? 3. Is the leading coefficient positive or negative? So look at the right side. Is it going up or down? It's up, which tells you that this is positive. Yes?
When you wrote x equals negative infinity on the top.
X goes towards negative infinity?
Yeah.
Yeah.
Are you supposed to write that one on top?
It doesn't matter. You have 2 sentences. I just need the 2 sentences. The top one is a sentence. The bottom one's a sentence. Doesn't matter which one you tell me first.
Okay.
Does that make sense? As long as they're both there. As long as you tell me how x moves to the left and as x moves to the right, you have to tell me what f of x is doing both times. So it's like saying 2 sentences. It's like telling you that my name is Mrs. Fox and I'm 30 years old, or I'm 30 years old and my name is Mrs. Fox. It doesn't matter the order I tell you those 2 things in. They're 2 facts. Does that make sense? Okay. All right, so let's look at this one. Let's describe the end behaviors there. So as x goes towards the left, f of x goes towards something, and as x goes towards the right, f of x has to be going towards something. Let's figure out which ones they're going towards. X goes towards negative, that's to the left. Which way is your y values going when we go to the negative side? Which way does your y value go? On the left. Down, which is towards negative infinity. On the right side, as x goes towards positive infinity, that's as you go to the right. So as we go to the right, where are your y values going towards? Positive or negative infinity? They're going down, so that's towards negative infinity. Okay. The ends, are they doing opposite things or do they match? They're matching, so they're even. State the number of real zeros. How many times does this hit the x-axis? Twice. Is the leading coefficient positive or negative? Look at the right side. It's going down, which tells you it's negative. Okay? That's everything for your notes. Now the assignment has problems very similar to all of these ones that we've just done together. Okay?